let's look at the complex power, and the basically we want to use the phasors and the voltage phasor and the current phasor to figure out the power. And let's see if we can so the voltage VA, voltage VT is equal VA times cosine omega t plus theta V, right? And in the past we use the phasors, and we always have VA is equal, we use VA and the phase angle. Now we are changing that to, we're using the VRMS and the theta V. So this is the phasor in RMS value. And so this is slightly different from what we used to have. We used to have just VA as the magnitude, right? Now we have the VRMS as the amplitude, and if we as the magnitude for the phasor. And if we use this, we don't really need to carry that half all the time, right? So let's see, we use the current also, we use the RMS. And the current phase angle is theta sub I, and so this is also the phasor in RMS value. So either we use a subscript or we use the RMS in the unit to indicate this quantity is in RMS value, not in the peak value as we used to. And let's see, if we define these, let's take the complex power is then the complex power, we use S, capital S, to denote the complex power. That's going to be equal V times I conjugate. And remember the conjugate for the rectangular form, you just flip the sign of the imaginary part, right? For the polar form, just change the sign of the angle, because the conjugate is basically the complex number that's mirrored across the real axis or the horizontal axis. And if we take this the conjugate of I, we get VRMS. The angle is theta V times IRMS times the angle of a negative theta I, because of the conjugate, right? So therefore we get, based on Euler identity, we have VRMS times the IRMS times the cosine theta V minus theta I plus J sine plus J VRMS IRMS times sine theta V minus theta I. So if we remember, and this quantity here, this is the P, right? And this is the Q. So the S is basically equal P plus JQ. So that's why the active power also called the real power, and the reactive power Q also called the imaginary power, because P is the real part of the complex power and Q is the imaginary part of the complex power. Right? The absolute value S is the apparent power. And the S is equal to, based on the what we learned for the complex number in rectangular form, that should be equal to square root of P squared plus Q squared, right? And also if you take the polar form, just take the magnitude, this should be equal VRMS times the IRMS, right? So that's the complex power. And what else? So if you look at these, and you can also see the S is also equal to the S, because the P is equal VRMS. Now the P, we can write the P is also equal to, we can write these, P is equal the apparent power times the cosine phi, or that's equal the apparent power times the power factor, right? And the Q is equal to the S times the sine power factor. So this could be plus or minus 1 minus PF squared times the apparent power, and if the so the plus sign for lagging power factor, so the plus sign for phi greater than 0, and the negative sign for phi less than 0, or the leading power factor, right? So because the leading power factor, you have a negative Q. You have the Q being negative. Okay, so that's the concept. The algebra is not that bad, but there's a number of concepts here. So I hope you spend a little bit more time to understand these concepts. And let's see, we have the example here, how we calculate the various quantities. So what I'm giving here is the voltage, phasor voltage across a load. What I'm saying here is I have Z sub L, the load impedance, and the voltage across this load is just the V, and the current through the load is I, and the current of I and V, they're following the passive sign convention. And I give you the voltage, and also I give the real power delivered to the load, and also the power factor is 0.8. That's a lagging power factor. And the first thing is, what is the apparent power? S, right? So the PF is 0.8, and since P is equal to S times the PF, so very quickly we can find S going to be equal to P over PF, and that's the number, that's a 2 over 0.8. That's not too bad, the number, that's 2.5 kilowatts. Right, so that's for the first one. That's quick and easy. And second one, what's the Q? And first we need to determine Q is positive or negative. So the power factor lagging Q is positive, right? Because the PF lagging, and the P is Q. Power factor the lagging, that means Q is positive. So therefore Q is going to be equal square root of 1 minus PF squared times the S, which is equal to square root of 1 minus 0.8 squared. And by the way, that's a nice number, 0.6, I believe. And the square root of that is 0.6 times the S is 2.5, so that's 1.5, right? And the unit is going to be kilowatts for the reactive power. What I'm doing here, the unit for the S is kVA, not watts. Right? For the P is watts. For the real power is watts. For the complex power or the apparent power, the unit will always be the volt amps, just a VA. Okay. And now the complex power. The complex power just equal Q. The P is just equal. The S is equal P plus JQ, right? So that's equal to 2.5 plus 1.5 J. The unit would be kVA as well. And the current, and to find the current, and number 4, let's see what's the voltage. Okay. So the remember the S equal V times I conjugate, all in phasors, right? not V conjugate, V times I conjugate. And so therefore the I is going to be equal to S over V phasor, and then take the conjugate, right? And so this will be the S conjugate over V conjugate, and S conjugate is going to be equal to 2.5 minus 1.5 J. Remember, I need to multiply by 1,000. That's the kilowatts, right? And the unit for the volt is the volts. So that's 120. The angle here would be negative 30 degrees because I'm taking the conjugate also. And the calculation here, the final value I calculated, that's 20.83, and the phase angle negative 6.9 degrees. And this, of course, this is the amps, and this is the amps in RMS value. Because V is in RMS value, right? I think V is indicated here. This is in RMS value, so therefore the current also is the RMS value. And now we will need to find the load impedance, and Z sub L is just equal to V over I, right? And I calculate this one. This give me 4.61 plus 3.46 J. Let's write it this way. This many ohms. That's it. That's for the complex power, how we can calculate using the various quantities. And if you're given V and I, you definitely should be able to calculate the complex power, the P and the Q, power factor, all these things, right? And this just the basic things for the power system. So, and next lecture we're gonna start looking at the single phase systems. Okay, and that's it for today's lecture. Only 2 video clips. Remember, no matter what you do, you just need to keep going, right? Never stop. I'll see you next lecture.